There. And now let's start the class. Okay, hoping everyone can see my screen. Yes.
Yes, sir.
Yes, it is.
Yeah. Okay. Okay. So again, we are going through a very sort of abridged summary of how action potentials are generated. This may seem a little overwhelming for those of you who are seeing this for the first time, because you know, usually cover this in about 6 classes in the uh, other neuroscience course. So if you have any questions, please stop me and ask. So this is what we did in the previous class. We looked at the structure of the neuron and how each neuron is connected to another neuron, and the chain of events that leads to the generation of an action potential, which then goes and at the synaptic terminal releases neurotransmitters, which causes some depolarization. And if that depolarization is enough, the next neuron then fires an action potential, and that's how information passes from the sensory, from the peripheral system, like the eyes, ears, and so on, to the brain. So then we started talking about the structure of a neuron and the intra and extracellular medium, and the fact that the concentration of ions are different across the membrane. We looked at the Nernst's equation, and we looked at what happens at steady state, resting state, when multiple ion channels are open. At that time, none of the ions are actually at equilibrium. Okay, so only when the cell is at the equilibrium potential of a particular ion, that particular ion is at equilibrium. So when your resting state is between EK and ENA, then neither EK nor ENA are at equilibrium, which means that their currents are not zero, but the sum of the currents that you see here is zero. That is why the potential remains where it is, and it would stay like this. It wouldn't stay like this forever, because current is going from one direction to another continuously, and then the concentration gradient will be lost eventually. So we have got pumps that maintain the concentrations or to where they are. Okay, so in the resting state, the potential is about minus 60 millivolts. So this now I can go back to this first slide that I had shown you here. So notice this plus and minus that you see is essentially because of that. So if I didn't have any ion channels that are open, the both sides, the extracellular and intracellular regions, are typically balanced in charge. You can't say that, oh, potassium is 145. These numbers are all different, but that doesn't mean that it's the chloride here that is balancing the sodium and so on. Okay, there are other charged particles, proteins and amino acids, etc., that make sure that in general the net charge on either side is zero. In general, if the ion channels are closed, and once you open one or a few ion channels, there's some movement of a few ions here and there that will set up this imbalance, and consequently a difference in charge, and consequently a difference in potential across the membrane, which will then balance out the concentration gradient. Okay, so that is why you have slightly negative charge here and positive charge here, and that's because the inside of the cell is at minus 60 millivolts here. So now the question is, this is a question to everyone, why is this VR, resting membrane potential, at this particular value, minus 60? Why is it not at 0 or plus 20? What determines between EK and ENA where this potential is eventually going to settle. Can anyone think?
The concentration of sodium and potassium?
No. So the concentration of sodium and potassium actually just determines EK and ENA. So once you have the concentrations of sodium and potassium in and out, you put that in, and that just gives you EK and ENA. I'm asking, when both of them are open, the resting membrane potential is going to be between these two, but where? Should it be at the midpoint? Should it be close to ENA? Should it be close to EK? How do I know where it's going to lie?
The number of sodium and
The number of ion channels.
Very good. So that's part of the answer. So number of sodium and potassium ion channels, as well as how easily they can let sodium and potassium through, right? So if you have got a ton of them, but they are very hard to, open, for example, then it won't help. So all of this, how easy it is for an ion to pass through a channel when it's open is captured in a very simple way in the conductance of an ion channel. Okay, so it's basically saying that if I open, how easily can current pass through? If the conductance is high, then for a given potential difference, the current is going to be high as well, because it's very easy to pass through. So for a given voltage, it's easy to pass through. So it's basically, in physics terms, going to be the permeability of this. So there are actually two different equations. One is called the Hodgkin GHK, Goldman-Hodgkin Katz equation, which is based in terms of permeability and so on. And the simpler one, which is I'm going to deal with, is just in electrical engineering terms, where we use a resistor which determines how much current is going to go through a particular ion channel when it's open. Okay, and they're equivalent in the sense that if the permeability is high, then it's easy for an ion to flow through the ion channel, which means that the conductance is high. So all the stuff that I have talked about so far in the previous class can actually be very easily summarized by considering the membrane as a battery and a resistor. That's it. So each ion channel contributes a battery, which is its equilibrium potential, which means that when the membrane potential is equal to the equilibrium potential, the current through it is zero, because the current that's going to go through is just Vm minus ENA, which is the potential difference across this, multiplied by the conductance, which is given by GNA. Okay, and the whole thing actually is as simple as this. This is how I get to the resting membrane potential. I say that, okay, at the resting membrane potential, none of the currents are themselves zero, but their sum is zero. And each current, the current flowing through each of these ion channels is just whatever is the potential difference, Vm minus E of that ion channel, multiplied by the conductance. This conductance actually captures the permeability, including how many ion channels are open, how many ion channels are there to begin with, and so on. All of that gets captured in G ion. So if you plug all of that together, Gk multiplied by Vm minus Ek plus Gna multiplied by Vm minus Ena, blah, 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 and then separate out Vm, this is what you end up getting. Okay, so it's actually quite remarkable. In fact, you don't really even need the three, GK, GNA, GCl, these are three different ion channels. You can actually consider them as a single conductance. This is coming from here, whose total conductance is given by this. It's the sum of the three conductances, and a single battery which is equal to the resting membrane potential, which is about minus 70 millivolts in this case. So all the complicated stuff that I talked about in the previous class eventually is getting reduced to a single battery and a single resistor, which for some reasons that I'll get into is called the leak conductance and the resting membrane potential. Okay, that's it. There's nothing else. This captures, in a sense, everything that we have talked so far. So any questions on this?
Sir, why the polarities of the batteries are different?
Yeah, so it's a matter of choice, really, how you want to show it. It depends. In this Candle and Schwartz book, they have flipped it so as to make the so it's because Na is actually positive, so and Ek and ECl are negative. If you look at these things here, Na is positive and K and Cl are negative and VCA is positive. So you can either call it, an unflipped battery whose voltage is, or an unflipped battery whose voltage is negative, or a flipped battery whose voltage is positive. It's just a matter of convention. That's it. So don't pay attention to this. The way this math plays out here, actually we are considering all the batteries to be pointing in the same direction with the values either positive or negative, minus 50, minus 90, plus 50 and so on. But equivalently, you could just consider the magnitude of that value and flip it around. Either way, you get the same answer. So it's just a matter of convention. Don't read too much into it.
Got it. Thank you.
Yeah. Okay. So here's a question. So suppose I take this membrane, okay, and I inject current into it. Don't worry about how I manage to inject some. So let's say some constant current and I am injecting. Okay, so there are actually devices that can, inject a constant amount of current into a cell. Don't worry about how I get such a current generator. Suppose I have one and I inject some current into the cell at some time and it's constant current. The question is, how do you think is the voltage going to change across the membrane once I start injecting the current?
My guess is that at first the voltage would start to rise or fall depending upon the polarity of the circuit, and then it will get saturated at a constant level.
Well, no. So that scenario will come to that later. This is a actually difficult question, but the answer is that the voltage is going to just jump instantaneously to a different level, which is basically coming about because now there is a constant current through this resistor. So whatever the voltage was at resting state, right, at minus EL, it's going to become EL plus R into whatever current you are injecting, where R is given by 1 by GL. Okay, so in this circuit, as soon as current starts flowing, there is a voltage difference across the resistance, which is just given by the product of the current and its resistance. Okay, or equivalently, the current divided by the conductance. So this current is constant. So on top of this battery, if the current is going this way, there's going to be a drop in potential going from this way to that way. That's how it works, right? The voltage difference across a circuit here is just the product of the resistance and the current. So in this case, if I start injecting current into the cell, the potential is just going to jump. Okay. So I will show this in more detail in just a bit, but actually if you start injecting current, you don't see that. And the reason you don't see that is because there's another element that we need to worry about, which is the membrane's capacitance. Okay, so this is the thing that sort of changes the game a little bit. In very simple terms, a capacitor is a couple of plates which are very close to each other, such that you can deposit some charge on one plate and suck out an equivalent amount of charge from the other side. So usually one side is plus Q, the other side is minus Q, but they are always balanced. So in effect, you can think of current passing through a capacitor, which is given by this formula here. Okay, it's a little bit tricky to understand. Those of you who haven't seen capacitors before might be very confused right now. I had told you earlier that the membrane doesn't let any current through, right? Because it's hydrophilic, and unless you have an ion channel, nothing flows through. That still holds. It is still the case that there's no physical ions that are moving through the membrane. However, the charge can get deposited on one side and get sucked out from another side, giving you an appearance as if charge is flowing through it. Okay, and the ability to hold charge is the product of the voltage difference around it and what is called its capacitance. Okay, so if you want to hold a lot of charge around it, you need to have a lot of capacitance. So back in the days, we used to have capacitors that are, like as big as this room. Maybe it's all, they're used now also. So you'll have to have very big plates which are separated by very small distance to have large capacitance. Generally, when electrical engineers use capacitors that are small in size, we're talking about, microfarads or nanofarads of capacitance. Okay, so basically, that's all I'm going to talk about the capacitor. It's another element that I need to consider. So a membrane is actually described by this little circuit here. There's a capacitor, a resistor, and a battery. Okay, and if I start to inject current through a capacitor, this is again the same question that I had asked. What happens if I inject current into the cell? Again, don't worry about how current is getting injected. Then the voltage is actually in this case is going to just change linearly. It's not going to jump anymore. Whenever you have a capacitor, voltage cannot jump anymore because then its derivative becomes infinite. In this case, if I is constant, then V is just going to be I multiplied by T divided by C. It's going to increase linearly because because its derivative is constant, which is given by the current. Okay, so I have two elements now. If I inject current through the resistor, voltage is going to just jump to whatever it was plus R times I. If it's through a capacitor, it's going to increase linearly. Any questions on this? This fine? Okay, so here's what happens when both are there, which is generally the case. If I inject current into a cell, the voltage initially starts to increase linearly. Okay, it is linear to begin with because when I just injected the current, there was no potential difference across this. So nothing was flowing through the resistor. All the current was going through the capacitor. All the current goes through the capacitor, charging one plate relative to the other, and thereby now bringing a potential difference. So initially the potential starts to rise linearly. But as now there's a difference in potential across the membrane, some current is going to flow through the resistor now, through the ion channels. This is what brings this down, and eventually it just settles down. And if I let this current flow through forever, all the current would eventually be flowing through the resistor, and the capacitive current would just fall to zero. The capacitor would hold some charge, and that would correspond to the potential difference that is developed across the membrane. And if you work out the math, it's very straightforward. It's C dV dt plus V by V multiplied by GL is equal to the total current. And if you solve that, you get something of this sort. So this is exponential charging and discharging once the current is taken off. So in other words, if I'm able to inject constant current into the cell whose magnitude I vary, the cell is going to charge and discharge in an exponential like fashion. Okay, and this is nothing but solving a simple differential equation. I'm not doing it here. And the time constant of charging and discharging is going to depend on the resistor and capacitor. It's tau is equal to RC is the membrane time constant. This is when the resistor is a resistor, which means that its value doesn't change as you change the potential across the cell. It's a true and well and true resistor whose resistance is fixed, which doesn't change on depending on the voltage. And as we will see, that things get very complicated when that condition is relaxed. Okay, so this brings us to the end of the first part, which is talking about passive properties of a cell. Passive property just means that the resistor is passive. It's not changing its value depending on the voltage or some other properties. It's a fixed thing. And if that is the case, if you inject current into a cell or into a neuron, its potential is going to either go up or down depending on the direction of the current, but the charging and discharging is going to be exponential. Okay, any questions on this? Okay, everyone seems happy. So I
Hello.
will, yeah.
Very small question actually. The thing is that charging is occurring. That means it is uh, accumulating the charge here inside the membrane, and during discharging, it is firing the action potential, right?
No, we haven't reached action potentials yet.
No, I'm talking in general manner. If you
We
can
will
just
get to that. We'll get to the action potentials when we get to it. Right now, there's no action potential. Right
Okay.
now, I'm saying is that if you inject current, it's going to charge and discharge in an exponential like fashion.
Okay.
Okay.
Fine. That is
Now we'll get to the action potential. Now that you mention. So this is what actually happens in a real neuron. So you are injecting current pulses, which are either negative current pulses or positive current pulses. A negative current pulse essentially hyperpolarizes the cell, which means that the potential goes down even further from this -65, which was the resting state. And if you inject more current, it's going to hyperpolarize more. This is following the RC behavior, which I had discussed here, right? So nothing surprising there. But now let's start injecting positive current. So we are depolarizing the cell. For a while, it's going to just remain in that RC-like fashion, charging on discharging. But something absolutely magical occurs once the depolarization reaches some threshold value. What happens is that if so you're stimulating and recording from the cell. If you reach a particular threshold, suddenly the potential just spikes up, zoop, like that. And then suddenly, immediately afterward, it comes back. This is a very non-linear sort of a behavior, that you just cannot explain using the math that I was talking about. There's something really magical that has happened. This is called an action potential. Okay, so what is action potential? It's a sudden change in the membrane potential whereby it suddenly gets hugely depolarized, almost reaching the equilibrium potential of sodium. But then it again comes back. Suddenly, for a while, it's hyperpolarized, and then it sort of settles down to its resting membrane potential. If the current is, if the current is, not maintained. If it is maintained, then it will actually generate potentially multiple action potentials. Here, what you are seeing is, as I'm increasing the current, now the number of action potentials is increasing, but the magnitude is not changing. This is very important because, as we will see later, the action potential magnitude actually doesn't change. It's only the number of action potentials that changes, even if you record at different positions from the neuron. Okay, and this is what allows us to convey the disturbance that is observed at one part of the neuron to be conveyed to another neuron, which could be several, uh, could be really long away, even a meter away, for example. Like, for example, there might be a neuron in your foot which has to convey that you stepped on, a nail or something. That information needs to go to the neuron which is in your spinal cord. So there's a long neuron which is sending information from your foot to your spinal cord. So it's as long as your leg, and it's still going to be able to do that because the action potential that are generated at the foot don't attenuate if as it goes along from the foot towards the trunk. The magnitude is maintained, and it could be an elephant's foot for all you know, or an elephant's trunk. It would still work because the action potential magnitude remains fixed. It doesn't change with distance away from the current injection site, which is not the case for a passive circuit. I didn't talk about passive propagation in this class, but in a passive case, the fall off with current injection site and distance is exponential, which means very quickly the disturbance is lost, but not in case of an active case. Okay, so in the remaining part of the class, I'm going to explain what an action potential is and how it works. Again, as I mentioned earlier, I'm going very fast here, especially because, we want to discuss the signal processing related to action potentials, not the biophysics in that much detail. Having said that, if you are getting lost, please stop and ask questions. I can't see you guys, so I'm sort of unable to gauge whether this is making sense. So it's your responsibility to sort of stop and ask if you are confused. Okay, so let's get to the action potential. So how do we understand an action potential? As I mentioned, something very nonlinear has happened here. If I look back at the circuitry, which I had shown, actually the only thing that is changing is that the resistor here is no longer a fixed quantity. It changes over time, which means that even if I want to measure this resistance, I won't be able to do it. Okay, so in my case here, if it's passive, it's very easy for me to measure the resistance. I hold the potential of the cell at some value, okay, away from the resting membrane potential. Let's say I say 0 millivolts. So I hold the potential at 0 millivolts, and whatever is the current flowing through, I can measure that, and the resistance is just Vm minus Vrest divided by the current. Resistance is voltage difference divided by current. Very easy. Suppose I try the same trick here. I hold the potential to a particular value. However, now there are going to be very complicated things going on. If I hold the potential of a cell, so suppose I depolarize it to 0 millivolts. Depolarization is just a fancy word for making the membrane more positive compared to its resting membrane potential. So R values more than minus 60 millivolts is depolarization. So suppose I depolarize the cell and I start to measure the current. If it's a passive circuitry, the current is going to be constant. It's just the voltage difference divided by the resistance, as I mentioned earlier. In this case, in an active case, things are very complicated because as soon as I depolarize the membrane, it's going to open up a bunch of sodium channels. Okay, this will increase the conductance of sodium, but because of that, more sodium will come in and it's going to cause more depolarization. This actually is the loop that causes the potential to just spike up like this. Once it reaches a threshold, sodium channels start to increase, sodium conductance starts to increase, which means sodium channels start to open. As soon as they open, all the sodium that's outside starts getting sucked in. One second. Laser pointer. Yeah, should have done that earlier. As soon as it reaches a particular threshold, sodium current starts, sodium conductance starts increasing. All the sodium starts going in, but when sodium goes in, the potential increases further, and that causes more sodium channels to open. Then it starts to increase even further, and so on. So it's like a vicious cycle here. If you hold it at some value, you won't continue to hold it at that value because the potential is going to change as more and more sodium comes in. So how do I measure the currents while keeping the membrane potential fixed? That's a very difficult thing to do. And part of the success in our understanding of how action potentials work is because some very smart people figured out a way to hold the potential fixed and measure the ionic currents. It's a technique called a voltage clamp, which I'm going to talk about now. So I should mention here that the story of this, our understanding of action potentials is an absolutely fascinating story. In biology, I can't think of another story that sort of matches in elegance and design and just scientific enterprise. The way some very smart people figured this out. The smart people that I'm talking about are Hodgkin and Huxley here. There were other people involved as well, like Kenneth Cole, who developed this. And Hodgkin and Huxley modified it. There were Katz and some other people who were involved. But the story that I'm going to talk about is the story of Hodgkin and Huxley. And they actually were able to not only explain how an action potential is generated, they even came up with a model that that is still used to this day. It's called the Hodgkin-Huxley model, which made some very bold assumptions, and at the end of it, they were able to explain the shape of an action potential, its propagation speed, the currents that are flowing through it, and so on. In enormously, it's really amazing that they were able to do it with the type of instruments that they had. So it's a story that every scientist should just read and be inspired with. It's really beautiful the way they pulled it off. Okay, so I'm going to just give you a very short preview of it. But if you have some time and you want to read about this won't be a waste of your time. You'll really love it. You can actually, for example, just look at these movies which sort of replicate the kind of things that Hodgkin and Huxley did. And you can just appreciate with so rudimentary, recording devices that they had, they were able to explain the action potential in you know in a lot of detail. It's really amazing. Okay, so back to where we were. I'm going to explain what's a voltage clamp. A voltage clamp is a device which allows you to clamp the voltage across a neuron at some pre-specified value that you get to choose. So I can say like, okay, I'm going to suddenly hold the cell at 0 millivolts or here 50 millivolts and keep it there for 10 milliseconds and bring it back. Or it could be a sinusoid, it could be a triangular function. You decide what the potential across the membrane is going to be. You can fix it. This is set here as the command voltage. So you are commanding the voltage that's going to be across the membrane. Okay. And as you have this voltage across the membrane, ion channels are going to open and close and do weird things. So the conductance is going to change and so is the current. So I want to measure all that current. That is what a voltage clamp lets me do. So to do this, I first of all need a very big neuron, a big axon to be particular, in which I can insert two electrodes, not one, but two electrodes. One is called just a measurement electrode, which measures the membrane potential, nothing more. The other one, this yellow one here, is called the current passing electrode. This is the electrode that passes current. You need both of them for this thing to work. So it's actually very elegant. You take an axon from this squid, which happens to have a very, very large axon. Thanks to this axon, that it's almost a millimeter thick. So you can actually put two electrodes inside the axon. So this fat axon that we got from squid is used. You put two electrodes. I measure the voltage across the membrane. So this is the reference electrode outside. This is the voltage inside. This is my VM. And I compare it to the command voltage that I am choosing. So the voltage clamp amplifier compares membrane potential to the desired command potential. And this device is cool. Whenever the measurement voltage is different from the command voltage, it sends some current. Whenever VM is different from command potential, the clamp amplifier injects current into the axon through the second electrode. This feedback arrangement causes the membrane potential to become the same as the command potential. This is going to inject current until it becomes the same, which happens very quickly. So essentially, as the membrane potential changes here, so does the conductance. So more current needs to go through to maintain the potential at the same level. This current passing electrode provides that current. So it provides that current so that the membrane potential can stay where it is. And the current that is flowing back into the axon and thus across the membrane can be measured here. So you can measure the current that is required now because of the change in the conductance across the membrane, because it's the same current. The current that flows through the membrane is the same current that is being sent by the voltage clamp amplifier. So this elegant system here will fix your voltage membrane potential to some fixed voltage that you choose, and whatever is the current and the conductance change that is required can be measured here. Okay, everyone gets that? It's very elegant, very cool. So let me just show this current to you guys so that it will make sense. So this is
Sir,
the squid.
excuse me, how they are measuring conductance? I didn't get that.
Yeah, I will get to the conductance. Right now, I was just talking about the current. I'll get to the conductance in a bit. So this is the giant axon. So I'll get to your question. Let's see what happens when I'm doing this. So suppose I just inject a little bit of current. Sorry, not current here. I'm not injecting fixed current here. I'm holding the potential to some value. So from minus 60, which was the resting state, I say, okay, membrane potential, now you're going to be minus 50 for this amount of time. Okay, the plot below is just the current plot. This is the total current that is flowing through the membrane. So you see there's a little bit of a blip here. This is just the capacitive current because of this change here. There's a sudden change, so dVdt is large, so the capacitive current is there. But then the voltage stops changing, so the capacitive current becomes zero. Blip is seen here as well. But otherwise, the current that is flowing through is flat. And what is this conductance? Conductance is now just voltage divided by this current. So it's flat. This is where the active mechanisms haven't kicked in and the current is just flowing through the leak conductance, which we had shown earlier. This is the passive part. Okay, so this is the stuff that we had talked about earlier. Here's the more fancy stuff. Now I'm holding the potential to a very depolarized state, 0 millivolts. Now there's a capacitive current as before, and it should have flattened out like this if the circuit was completely passive. The current just would have been the voltage difference here multiplied by the conductance, which hasn't changed. So as you increase the voltage, this current should have just scaled up. It should have been a scaled up version of this. But instead, it shows this very peculiar shape. It just dips down and then goes up. Okay, and this is because the conductances are changing as a function of time. They are no longer fixed. Okay, so as somebody asked, how do I measure the conductance? I'll get to it. It's actually very straightforward, but try to appreciate this for now. The membrane potential is held to a constant value 0, and the membrane current is showing a very peculiar shape here. And it's not a straight line, which we would have expected if the conductance was not changing. Okay, so now I've got this funny shape. What do I do? Well, I want to first find out this total current in the membrane is the sum of all the ionic currents, right? So I want to find out how much current is flowing through the sodium ion channels, how much is flowing through potassium ion channels, and so on. And in fact, it's not very hard to do. There are certain chemicals that can block one of the ion channels. So for example, there's a tetrodotoxin here, which is produced by a fish called puffer fish. It's lethal if you get, if you eat this fish without treating it first, the tetrodotoxin will kill you immediately. But people figured out a way to clean the fish properly, and it's actually a delicacy. It's called fugu in Japan, where people eat puffer fish, which has been, you need proper licensed chefs to clean it properly, and the king of Japan can't eat it because what if the fish is not cleaned, and so on. People actually die of puffer fish poisoning as well, but it is it is considered a delicacy. So if you can isolate the toxin and put it in the bath, it will just remove all the sodium current. And if you repeat the experiment, the curve will change like this. This is the current measured in presence of tetrodotoxin. This is the potassium current, and this is the sodium current. It increases and then this goes down. And this can be measured in presence of another chemical which blocks potassium, so that you can measure the sodium current. Okay, and if you add them up, you will end up getting something of this sort. Once you isolate this, actually the conductance is trivial to find, because as I mentioned, the conductance is nothing but voltage difference divided by the current that is going through. No, so that's resistance. So,
Sir,
sorry.
doubt.
Yeah.
In the previous slide.
Yeah.
Again, the previous one. So in that there is like a downward inward current, right? When
Yes.
so now if the sodium channels are blocked, so how do we get a downward inward current in that case also in tetrodotoxin?
So in the presence of tetrodotoxin, you get this. You don't get that. Presence of tetrodotoxin is the potassium current which is upwards.
Okay, so that's the condition when there is no. Okay, got it. Got it.
Okay.
Got it.
So now the circuitry has changed. You have a capacitor and the leak currents as before, but you've got now voltage gated ion channels, sodium and potassium. So now there are conductors which vary. And if I do the same experiment, I get the current, and the voltage divided by this current is the resistance. So the current divided by the voltage that I'm holding, now the voltage is not changing, it's fixed. So the current divided by the voltage is just the conductance. So it will have a similar shape. That is why it's trivial to compute the conductances. Okay, it's basically the same shape as the current. You're just dividing by the voltage, which is anyway fixed. So there you go. This is how you measure the conductances of sodium and potassium in the active condition when they depend on the voltage. Okay. So here's the cool part. Okay, and I think I'm just going to summarize it a little bit here rather than going through the details. Basically, what happens is when a cell is depolarized, the sodium channels get activated and they open. So the sodium conductance shoots up. This causes a massive depolarization in the cell, and the potential starts to reach the equilibrium potential of sodium. However, there's an interesting mechanism that causes these sodium ion channels to inactivate after a while. And this is just a function of time. After a while, they start to get inactivated. So their conductance starts to fall. And the other thing that starts happening is that the potassium conductance starts increasing. So the sodium channels open quickly, the cell depolarizes, and then the sodium channels begin to close and potassium channels begin to open, and then the potassium starts coming in. The potassium starts going out. Sodium came in, potassium starts going out, which causes the membrane potential to again fall. And that's what generates the action potential. Okay, so I'm going to skip this much. And it's really a little bit advanced there. But this is the sodium ion channel. It has two types of gates, the activation gate and an inactivation gate. When the membrane is depolarized, so the inside is positive and outside is negative, this activation gate opens, sodium starts coming in. But this ball-like thing will come and eventually gets plugged here. This happens even if you hold the membrane potential to the depolarized state. This will always happen. So the sodium ion channels will eventually get closed. And once they are closed, they are done. They are inactivated. This ball doesn't go out until the membrane is again repolarized. Okay, so if it's depolarized, it gets blocked and goes to this inactivated state. And only when it comes to a resting membrane state that this opens and we are back to where we were. Okay, and this together, see, this is Hodgkin and Huxley 1952. They were able to predict the shape of the action potential perfectly well. What is happening is that, so this axis is time, this is potential. Sodium conductance has increased, potassium conductance hasn't. So it's dominated by the sodium current here. Sodium comes in, the membrane gets depolarized, and here the sodium starts to shut down and the potassium starts to increase. So now this is mainly your repolarization phase, because potassium is going out and the sodium is not doing anything. And therefore the membrane potential comes down. Here it actually undershoots the resting membrane potential, which is because the potassium conductance is slow, so it's still open. But eventually, once you are back in the resting state, it will come back to the resting state. and all the conductances will become 0. And it's again the passive circuitry that we have been talking about. Remember that these guys get activated only when the membrane is a little bit depolarized. So all of this happens and you are back to square one. Okay.
Sir. Hello.
Yeah.
Yeah. Sir, I could not understand the connection between the thing that you were talking. The resistance is active or like it changes in the circuit. When you were explaining the circuit, you were saying that the resistance is changing.
Yeah.
And the connection with the actual neuron, like actual membrane, I could not get it.
So conductance, this thing changing just means that it's not constant over time. The leak resistance, if I plot the leak resistance, it will be a flat line. Okay, and it won't change depending on what the voltage is. It's just a, it's just a constant value.
Okay. In the neuron membrane, what is causing the change of that resistance?
So yeah, so that's where the dynamics of these things come in.
Okay.
The membrane potential. So this is more stuff that I wanted to show here. So in these cases, there are these gating particles that are also charged. So this ball is charged. So when this becomes positive, it sort of goes this way and yanks out this thing.
Okay.
The more positive you make it, the more ion channels are going to become in that open state. Okay, so these are the special gates that depend on what the membrane potential difference is.
Okay, and so basically because of the ion channels, the resistance
because
changes.
Of voltage gated ion channels.
Okay.
The resistance of the conductance of the ion channels change depending on what the voltage is.
Yeah. Okay.
And that is what is causing this action potential.
Okay, sir. Thank you, sir.
Okay.
Yeah.
So just one more thing before we wrap up for the day. So I've generated an action potential. You might wonder what happens if what happens after this, after it comes back to 0. Turns out that at this stage, you might think you're pretty much in the same boat as here before the action potential, but that's not the case, because the sodium voltage gated sodium channels here are in this resting state, but the sodium voltage gated, the same channels here are in this inactive state. And until this ball comes out, you won't get back to this state. And this ball takes a while to come out. So even if you inject another strong current pulse here, you won't be able to generate another action potential. That's because all the voltage gated sodium channels are blocked right now. They are in this inactivated state. So there will be some time before this neuron can again fire action potential, and that is called the refractory period. So there's an absolute refractory period, which means doesn't matter how strong is the stimulus, it won't generate another action potential. After that, you get into this relative refractory period where you need to inject a very large current in order to generate another action potential. And over time, it will go back to the normal threshold. Okay, so this is what prevents a neuron from continuously firing action potential, because it keeps going into this refractory period every time it generates an action potential. Okay, so we will stop for today. I'll take questions if there are any. I understand this is a lot of stuff that's sort of being thrown at you. Please, if you have any questions in the next class, beginning of next class, I'll take that. I'll briefly mention how action potentials propagate, and then we will start with the questions and the math that is needed to answer those questions. So we are almost done with the biophysics, and we will start with the signal processing and random variables shortly in the next class. All right, so I'm done for today. If there are any questions, please go ahead. Otherwise,